Okay, to introduce you to the Smith chart. The Smith chart is a tool used for graphical representation so that you can work out how the components of a transmission line network relate to each other. We start in thinking about the Smith chart by thinking about the reflection coefficient rho. Rho, if you recall, is the ratio between the reflected amplitude and the incident amplitude. It's a complex number. It has an amplitude itself that is less than 1, and it has a complex phase related to how far away from the actual reflection you are. We can plot the reflection coefficient on polar axes. Being a complex number, that's what we know as an Argand diagram, going back to your mathematics. So here we have the complex rho plane. Rho equals 0 is in the centre. Modulus of rho is this circle around the outside. Modulus of rho equals 1. Halfway we've got mod rho equals 0.5. The argument of rho gives you the angle. So if we have rho is 0.5 and a phase angle of 3/4 of pi, we would plot rho out here equals 1/2 minus 1/2 plus 1/2 of j. So this is how we plot polar coordinate for rho. That's what the Smith chart is. In the background of all of this, a polar plot of rho. As rho changes, as you move along the Smith chart, as you move along the transmission line, away from the load, and the load was where the reflection occurred, the local value of the reflection coefficient, which depends upon z, depends upon z over here like this. So you have the reflection coefficient at the load and a complex phase. This, you can see, is a complex number that runs around the origin in the complex rho plane. The phase angle is proportional to the distance moved away from the load. The distance is normalised by the wavelength, and this is very important, the wavelength in the transmission line. You actually have to work out the wavelength in the transmission line. Divide that and you get z hat. That's what beta z is up here. Once around the circle corresponds to half a wavelength. Remember, the wavelength of a standing wave is half the wavelength of the travelling wave. Because of the way we have set up our axes, as z becomes more negative, you get closer to the load. So we look at our Smith chart. Here we have the angle 2 pi. Once around the Smith chart, 2 pi equals 2 beta lambda divided by 2 equals it's lambda on 2. Our initial reflection coefficient over here, we've plotted it. Complex number in the rho plane. We are now going to move towards along the transmission line, towards the generator, a distance corresponding to the phase change of the angle, the phase change of our local reflection coefficient rho. So, where do we find this on the Smith chart? Likewise, if we go towards the load, in this particular case, we're going the other way around, you see, towards the load, this way, anti-clockwise around our Smith chart. Again, we've plotted the initial reflection coefficient. As we move towards the towards the load, we've gone our distance there. In this case, L is negative. Putting that together, we go to our Smith chart. Here we have written along the Smith chart the words wavelength towards the generator, wavelength towards the load. So to move around the Smith chart, the angle simply corresponds to the length on the transmission line divided by the wavelength in the transmission line. And once around is half a wavelength. So the complex row plane. Next thing to think about, special values. Special values are three special values. When the load matches the line, rho is equal to 0, so of course the point is in the middle, amplitude of rho is 0. Open circuit, rho is equal to +1. Short circuit, rho is equal to -1. Easy to plot those values in the row plane. Now we move to impedances, and this is where it gets slightly trickier. What are we actually plotting on the Smith chart? Because when you look at your Smith chart, you have all these other circles. This one here, and this bit here, and so on. What are those other circles? Well, first, to understand them, you have to remember how the reflection coefficient connects to the input impedance. The input impedance is a number that varies along the load, the effective load at a point. So the reflection coefficient, if you remember, pardon me, the reflection coefficient is Z load minus Z naught divided by Z load plus Z naught. Characteristic impedance of the transmission line, the actual impedance of the load. I'll get rid of those arrows so that we've got space back on our screen here. We can normalise the input impedance. The input impedance was a rather more complicated expression. ZL plus J Z naught tan beta L divided by Z naught plus J Z L tan beta L. Remember, tan is periodic in pi, not 2 pi, so once again the wavelength is half. This is normalised, divided by Z naught, the characteristic impedance of the transmission line. What we've done here is we've found the effective load impedance at position L, position along the transmission line, the effective load impedance at position L. We can replace the other load plus length of line with this new effective load. This value, Z hat, is a complex number. We get special circles for the real part of Z hat and the imaginary part of Z hat. See, it's a complex number. Z hat is an element of C. So it's a complex number. It has real and imaginary parts. Where Z hat is constant and where the real part and the imaginary part are constant, form a family of circles, which is what I'll show you next. Circles of constant resistance. Constant resistance. The resistive part of Z is the same everywhere on this circle. We don't know what the imaginary part of Z is, but the resistive part is the same all the way along here. Z equals 0, Z equals a half, Z equals 1, Z equals 2. The other circles are where Z is entirely imaginary. Z equals J2, Z equals minus J2. Remember, plus or minus is important when we look at the reactive part of the impedance. So these circles are the other circles on your Smith chart. You put them together and you start to see the shape that we've had previously. Circles of constant resistance and circles of constant reactance. Now, of course, you haven't got all the circles because your Smith chart itself is trapped inside mod rho equals to 1. Now I add the directions, the green curves that we had previously, towards the generator, towards the load, and put put the Smith chart in behind it, and you can actually identify the different things. Here's X, the reactive part of the impedance is equal to 0.5. You find 0.5 in small numbers on your Smith chart up here. This small number here is telling you that this curve is X is equal to 0.4. This curve here is R is equal to 0.1. There's the 0.1. 3.0 here is telling me about this circle is R is equal to 3. That's what we have. All of those circles index something. So you can interpret all the features on the Smith chart. Direction, what these numbers mean, what these numbers mean, and where the special values are. So, as an exercise, let's plot the value of Zn divided by Z0, move a specified distance, and we convert that to an angle, and we can directly read the new normalised impedance from the Smith chart. The example, the transmission line has a characteristic impedance of 50. The load of 50 plus J 50 ohms is attached. The wavelength in the line is 2 centimetres. In the line, let me stress that again, in the line. Evaluate the impedance 2 millimetres closer to the generator. Normalise the load. 50 plus J 50 divided by 50 equals 1 plus J. See, I always do numbers that work out easily. The distance to move is 2 millimetres divided by 20 millimetres. 2 centimetres being 20, and that's now in units of wavelength. We turn to our Smith chart, and you see the exercise. We plot 1 plus J up here, because we've looked for the circle R equal to 1, and the susceptance is equal to plus 1J, so we're on this curve, we're on that curve, they intersect at that point. Initial point, we move a distance 0.1, 0.1 towards the generator is this way, so our initial distance coordinate is up here, 0.16. 0.161 I would say. We move around to 0.261, which is this point here. We draw a line from the origin through there, intersecting this circle. So we draw that circular arc, intersecting that point, and we find that our new value, reading off the Smith chart, and I've got to rub this out so I can actually see what we're on. Circle in here is 2, there's 2, there's 3, so this is, it's about 2.7, 2.6, so R is equal to 2.6. Down here we're on the circle coming down here, which is following it down. The circle is 0.4 minus J 0.4. And I know it's not as close to the exact value as you'd get using MATLAB, but it's a quick way of actually evaluating what's going on. That's the final position there. The important thing being, from the diagram, you can show exactly how things are changing. Now remember, this is talking about impedances. If we're going to use admittance, what are we going to do? Well, the advantage of a Smith chart is that all you have to do to invert is reflect through the origin. Let me show you an example. Transmission line, characteristic impedance is 75, the load of 150 plus J 150 ohms. Determine the normalised load, and then use the Smith chart to determine a normalised admittance. Normalising 150 you divide by that gives me 2 minus 2j. So that's our normalised load. To do the exercise we plot 2, there's 2, so we're on this circle, that's the initial position, on that circle intersecting with minus 2j, which is this circle here. We reflect through the origin and we get this point here because we can look down here. This is on the circle 0.25 for R, and we follow out the circle 0.25j for the reactive part. And you can check with MATLAB and you find that you get exactly the same answer. So you're now able to interpret and use all the values on your Smith chart.